All right. So for today, some practical considerations. It's a slightly longer presentation, but it's just theory, and it's on the Brightspace as well. I think it has a different lecture number. It's like lecture 22 or lecture 21. A little bit of an overview of what we have done this semester and how this fits into a larger picture. Finite elements are a general technique to solve partial differential equations. That's why you should think about it. It's not just an elasticity problem or just a heat transfer problem. In general, most physics can be represented with PDEs, and then finite elements are a good way to solving PDEs. In this class, we have focused on particular classes of PDEs, mainly the heat transfer problem and the elasticity problem. Those are really nice PDEs. They are very well behaved because they are linear. So you end up with a linear system of equations. They are elliptic, which you don't need to know the details, but that just means that they are smooth. You get some smooth solutions. They are self-adjoint, which is just a fancy word for a symmetric operator. So you get symmetric stiffness matrices, and that is nice for the numerics. They are single field, and by that I mean like we either solve for displacements or we solve for the temperature. But there are problems where you want to solve for more than one thing. So, for instance, if you do a coupled thermomechanical problem, then you have not just displacements of not just the temperature, but you have a coupled set of equations. So we haven't done any of that. But that's finite element methods are also used for that. So again, we have kind of restricted our attention to a small subset of the types of problems that you can use FE for. For this type of problems, the FE leads to a linear system of equations, which is symmetric, is very nice numerically. And so if you solve it, you get a smooth solution. And this is the case for heat transfer or linear elasticity. But there are other types of problems for which FE can be used. A lot of problems. So I'm going to list a lot of them. And just to give you an idea, we're not going to go into the details and we're not going to solve this. But if you face them in the future, in your work or whatever, just to know that they are there and that there are things that you might need to consider to solve those problems. So for example, linear but incompressible elasticity, that is a type of problem that is very common, like rubbers, for example, are incompressible. That means that if you stretch them a lot, the volume doesn't change. And this is very different from, steel or aluminum, which have Poisson ratio of like 0.33. So those actually change volume. So they are compressible. But there are some that aren't. So if you just use blind FE for problems with incompressible, when the Jones modulus, when the Poisson ratio goes to 0.5, then you will not get the correct solution. There is this thing called volumetric locking. That's just a thing that happens in FE where, because there's not enough flexibility in the mesh to account for the changes in shape without changing volume, the elements themselves are unable to capture changes in shape without changing volume, then you don't get the correct solution. And Abacus, for example, has these things called hybrid elements. They have an H at the end. So we have used things like C3D8, that's the 3D hexahedral element. There is a C3D8H, which has an additional pressure field. So this one is a type of element that you would like to use if Poisson ratio is close to 0.5. Then you would want to not use the normal elements, but you want to use these hybrid elements. Then, yeah, this is what happens when you have incompressible elasticity. So when you use these hybrid elements, you have to be careful because you might get, this is the pressure field. And you have to plot your pressure field. And if it looks something like this, like the first one, for example, or this one, then you have to worry about that because this type of checkerboard patterns means that your solution is unstable for the pressure field. So you're not getting the correct solution. It should look something like this. It should look something smooth for the pressure field. So you get a pressure field that looks like a checkerboard pattern, then that means that you are having some instability on the pressure field. So you have to basically go back and try to find a different element that would work for it. Abacus mostly has this solved in, but just so that you are aware of this, that when you see something like this for a pressure field, then something is wrong. You should not get this type of checkerboard pattern. Other problems in solid mechanics that we didn't talk about, nonlinear elastic materials and nonlinear geometry. So if you look at the abacus when you try to set up your step, there's this NL option that we have never clicked. But if you have large deformations, then you have to click this nonlinear geometry. And then for the materials, we've only used the linear elastic materials, but there's a broader class of materials that are nonlinear. The simplest of the nonlinear materials are called hyperelastic materials. And then you can select when you choose a material in Abacus, typically you have done just material, elastic, that's it, linear elastic. But you can do material, elastic, hyperelastic in Abacus, and that's a class of nonlinear materials. Again, we haven't really done it in class, but this is what you should use for things like rubbers, for example, or tissues. Yeah, Abacus can do it, but we haven't done it. Another type of nonlinear behavior that you might get is when things fail or yield. So plastic or viscoelastic behavior, growth, remodeling, damage, all of those things can be done with Abacus, but we haven't done anything about it. But Abacus has built-in formulations for plasticity, for viscoelasticity, and the strong form is almost the same, but the constitutive equation, so again, the material model is not just stresses related to strains, but there is some history variables. So for plasticity, for example, there's a plastic internal variable per element that basically gets updated. And if there's plastic deformation accumulated over time, there's an extra variable that will keep track of that. So that's, again, something that you can solve with Abacus. We haven't done it, but just so you know that there are ways of capturing inelastic behavior, mainly plastic and viscoelastic deformation in Abacus. This is, for example, the type of work that we do in my lab. So this would be nonlinear large deformations for both things. There's large deformations and also the material is nonlinear, highly nonlinear. And so this is for this type of, I mean, it's clear that it's large deformations. And it's not clear that the material is nonlinear, but it is nonlinear. For those, you have to change two things in Abacus. Again, when you do the step, you have to click on the nonlinear geometry part. And then when you define the material, you have to not use linear elastic, but you have to use hyperelastic. Another problems that we didn't solve, but they can be done in Abacus is beams, plates, and shells. These ones, the strong form is actually different. For the other ones, for the plastic deformation or viscoelastic deformation, for the incompressible elasticity, all of those, the strong form is almost the same. The thing that changes is really the material model. For beams, plates, and shells, actually the strong form is very different. The strong form has extra derivatives, and we didn't really do this in class, but because of this, these are completely different formulations. Abacus can do them. It has structural elements for shells and beams, and the advantage of those is that, for instance, for the pressure vessel problem of exam 3, the Abacus exam, you don't even need to have, if you do it with solid elements, you have to have multiple elements through the thickness. But if you do it with a shell, you only need one element because they are already built basically to capture bending without the need to have multiple elements. Whereas in class, in your lab, I don't know which lab was that, 5, maybe lab 5, when you did the beam bending, to get accurate beam bending you need multiple elements through the thickness. But with shells, you only need one. So they are actually very, very efficient, but we didn't cover them. Another type of thing that we didn't do is dynamics. I think I mentioned this on Wednesday of last week, that the strong form changes a little bit because now the right-hand side has this inertia. This is no longer an elliptic problem, which means that the solutions are not smooth. There can be oscillations, waves, buckling, There can be shock wave propagation. And so yeah, it's a larger class of problems. In Abacus, you can do it. There are these so-called explicit or implicit methods. Again, we're not going to really talk about it, but that's yeah, that's the type of method that you would use to solve this. So if in any point, I think the rule of thumb though is that you can calculate the accelerations uh, or estimate them at least to see how big this term is compared to the internal forces for a given problem. And if it's big, then you cannot ignore. But if the accelerations are small, then you can do the static problem. So we've only done static problems, but yeah, again, that doesn't cover things like impact. Impact, then the accelerations are super high, so you cannot ignore this term. And then you will need to use explicit or implicit methods. Explicit methods, the advantage of them is that you don't have to solve a system of equations. You just need to integrate over time. The problem with them is that they require very, very, very tiny time steps. So you should use explicit methods if you are restricted to have small time steps anyway, or if you have a relatively short simulation. Implicit methods are better because you can are better for problems where you can take slightly larger time steps if you're interested in sort of a longer response. Use the Abacus documentation. I don't think I've used it a lot in the class, but there's no way we can cover all of the Abacus details in the class. So I think one thing that you should know how to do is after this class, obviously asking other people, but also checking the documentation. It has really good information about the types of elements. It has some hints as to when do they work, when do they not work, that type of thing. So just refer back to the Abacus documentation when necessary. Yeah, these are, for example, the shells. Like I said, this is basically you don't need multiple elements through the thickness. A single element through the thickness is enough. So they save you a lot of computational time. Another thing that you can use finite element for is modes of vibration. So if you do eigenvalue analysis, again, we didn't really do this, but you can do you can get the vibration modes. So that's very, very useful to try to get the natural frequency, to try to see if something will buckle, how it will buckle, if something will vibrate, what are the resonant frequencies of a structure. So Abacus can do this as well, but we didn't do it in class. But it can be very useful for problems that deal with vibrations, for example. Fracture Abacus can also do it, but we didn't do it. There's a couple of different ways of doing fracture. There's these things called cohesive zone elements and also XFEM. Very advanced topic. I would not do it without a little bit of more theory on fracture mechanics, but it's also possible. Also, you can do fluid mechanics with finite elements. Here, FE is not as common. So usually other finite difference schemes are more common to solve Navier-Stokes. And this is because the domain is generally constant. So when you are doing fluid simulation, usually your domain doesn't change. There's no deformation of the domain. So yeah, so typically you don't end up using finite elements. And these equations are also not elliptic, so there are many stability issues. CFD, computational fluid dynamics, is a field of its own. Abacus has some fluid capabilities, but in general, it's not. Abacus is not the top choice for CFD calculations. There are many other software that is used for computational fluid dynamics, and I would say Abacus would not be my first choice for that. These are instability problems. So this is you have to be aware of this type of problems. So if you look at this beam and you put a load on top of the beam, there's buckling. This is called snap through. So you have probably experienced that. You know, if you have a ruler and then you try to push it on top, at some point it will snap, right? So this type of snap through behavior are instabilities. What happens is that your stiffness becomes negative for a little bit before becoming positive. That means that there's a very large displacement without an increase in force. So when you hit that critical load, there's suddenly a big change in the deformation. You've done this for 323, where you have columns and the Euler beam buckling of columns, where you push normal, and then at some point it will buckle. And at that point where it buckles, the stiffness is basically zero because there's a large change in shape without extra force. It's just when you hit that critical load, then that large deformation occurs. In a displacement versus load plot like the one shown here, it looks like that. So you have an increase in load, and then at some point when you have this type of instability, this buckling or snap through, then you get sort of a negative stiffness, and that means just very large displacements without extra force. Actually, the force decreases eventually, and then eventually picks back up, right? But this type of negative stiffness or zero stiffness is characteristic of these buckling patterns. Your FE simulations will fail whenever there's this type of buckling. And there is ways of dealing with that. Do they have? I don't have it here, but there is ways of dealing with that in Abacus. In the methods, we didn't cover it, but when you're doing your static analysis, there is ways of selecting arc length method in your options for the step. Arc length method is a way of dealing with this type of buckling problems. So again, just for you to be aware that if you expect any sort of instability, your typical FE won't work, and it won't work because of the zero or negative stiffness, which means that your system of equations is singular. And so ways of dealing with that is in Abacus, there is this option called arc length method. So again, just for you to be aware of that circumstance. When can it fail? Yeah, this is like, again, sort of whenever you have this type of buckling, you should expect problems. Rules for finite element selection. Again, please refer to the Abacus theory manual. I would say my first choice would be quadratic reduced integration elements. I think that's typically a decent choice at the beginning. They have good accuracy, not crazy computational cost, good flexibility. Now, when you have large strains, if you use the reduced integration, we have seen this before, then you can activate some of these unstable modes, these hourglass modes, and then you might run into trouble. So again, look for how the mesh deforms, and if you see these hourglass patterns, then that means that you are activating these free energy modes or these unstable modes of the reduced integration element. So you just have to be careful with that. But you know, as a rule of thumb, I think the quadratic reduced integration are a good choice. You should also avoid the quadratic elements if you have complex interactions such as contacts, sharp corners, single point forces, or node-to-node constraints. Why? Because for problems that have contact or sharp corners or node-to-node constraints, then it doesn't matter if you use linear or quadratic, your order of convergence is actually the same. So then there's no point in using the quadratic elements, just use linear elements. Yeah, like it says here, these problems have singular stress solutions at the points where you have the contact or the sharp corners, and the degree of convergence is governed by those features and not by the order of the element. So using quadratic or linear does not make a difference. For the regions where you have stress concentrations, typically use full integration. So if you have a mesh and you know that in some part of the mesh the stress is not going to change much, then you can use reduced integration for that part. And then if you know that there's going to be a lot of stress variation in some other portion, then I would use full integration for that region. For large deformation, depending on the amount of distortion, you might be better off with linear elements. Quadratic elements are super accurate, but they really depend on the shape being high quality. That is, the shape has to be regular enough, because otherwise you run into problems with the Jacobian inside of the element. So even for quadratic elements, they should behave a lot better, but they are very sensitive to lash distortions. So you have to be careful with that. If you have a lash deformation problem, then you have to be careful when choosing quadratic elements. Depends on how much distortion you will have. They are a little bit less robust compared to linear elements. So linear elements are just a little bit more robust when distorted. So again, this is only applicable to lash deformation problems. Yeah, so there's always some trade-off. Linear elements, very robust. They don't have that much distortion. They are stiffer. You need larger meshes. Um, on the other hand, quadratic elements, they have more flexibility, but if you have bad shape, if they distort a lot, then you lose accuracy. So some trade-off between the two. Caution with reduced integration elements, they can have some similarities. We have seen this before, the hourglass shape or the zero energy modes. So when you see something like this, like the hourglass shape, in this region right here, that means that probably you are triggering some of these zero energy modes. So you just have to be careful with that. I've shown some of the examples before as well. Uh, when possible, use quadrilaterals and bricks, but it's not always possible. So a lot of the times, the only thing that you can use is triangles or tetrahedra. But these triangles or tetrahedra are usually stiff, so you need a lot more elements to accurately describe the solution. So I would say, if possible, do the squares or the bricks. And then if not, use the triangles, but then you need really fine meshes. And that's something that you get out of the mesh convergence analysis. As always, always do mesh convergence analysis. And you will see that when you use triangles or tetrahedra, you just need much finer meshes to get to get convergence, basically. Do not connect linear and quadratic elements. This was part of the question for exam 2. Yes, you can mix full and reduced integration. Yes, you can mix different elements of the same polynomial order, like linear triangles, linear quadrilaterals. You can do that. Quadratic tetrahedra with quadratic hex, you can do that. But just don't mix linear and quadratic. Mesh in a way that you increase the number of nodes near regions with high strain gradients. Use bias in the meshing. You have done labs about that. Check the quality of the mesh. The more for the quadrilaterals, the more of a square it looks like, or for triangles, the more of an equilateral triangle they look like, the better. So if you look something like this mesh will work, but this mesh is better. So the more they look like the aspect ratio is even, so you don't have really squeezed elements, the better convergence you will get for your solution. Monitor distortion, just check. There is some geometry checks in Abacus, and this is particularly important for nonlinear geometries. Like I said, if you use quadratic elements and you have lash distortion, typically your accuracy drops down. So you have to be careful with that as well. Yeah, so you typically do bias in the meshing, so try to mesh more near regions with higher stress gradients, less with regions with no stress gradients. There's adaptive meshing in Abacus. We didn't do it, we kind of did it manually, but there's some features in Abacus that will allow you to do adaptive meshing, which is that as it solves the problem, it will try to calculate where in the mesh should you have more stress gradients, and therefore you should refine your mesh. So it will automatically do that for you. We didn't do it, but there's automatic remeshing in Abacus, basically monitoring the stress gradients and increasing the mesh size in those regions where you have greater stress gradients. We didn't do this for the exam 2, but you could have done an axisymmetric problem. There's an axisymmetric element in Abacus. It really is just like a 2D problem. You just select axisymmetric. yeah, so instead of having to model the 3D part, you can just model a 2D part, and that's it. And it should give you the same as you do the 3D one. So you can do that in Abacus. There's contact problems. We didn't cover contact in class, but there is a couple of problems. There's this penalty method or Lagrange multiplier, and whether or not you add friction. So again, we didn't cover it, but that's another topic of its own. And then you can do it in Abacus. So there's some contact formulations in Abacus. So just for you to know. There's coupled problems. We didn't talk about this, but fluid structure interaction is a very, very, I guess, hot topic right now. Thermomechanics or other combinations of PDEs. Abacus has some capabilities to it, but it's not its main strength. There's other finite element analysis that really have focused more on that. I think COMSOL is probably the most common one of the finite element programs that has really tried to do coupled problems. So I would say, it has also its drawbacks, but it has really emphasized this idea of solving coupled problems. So I would say for coupled problems, maybe Abacus might not be the best option. That's it. I think that's a very short lecture, but I think that's good. I'll let you go on with your day early.